Today we're moving back into exponentials and we're focusing on how we can use exponentials in rates of change. So that's something that we did at the end of our last chapter. So what we're looking at for these is rather than using x and y, we're now looking at differentiating these with respect to time. So when we're looking at things that grow exponentially, we talk about the growth of bacteria, we grow a population, or we could have a population in decline. We also can talk about the increase or decrease in temperature of certain liquids. So if I were to boil some water and I leave it out, I'm looking at how quickly it cools down, or it could be a block of ice that I put out in the sun and I'm looking at how the temperature is increasing. So when we're looking at these things, we're looking at some sort of measured variable compared to time. So here's an example of the types of questions that you can get with exponential rates. So the growth of a population is modeled by this equation. So P for population is 30,000 e to the power of 0.1 t. And t is the number of years that have passed. So the first question we've got here is, what is the initial population? Now just be careful with this word. So there's no numbers in this statement at all, but there's actually a lot of numbers that are inherent to the question. The word initial means that we want t equal to 0. Okay, so at the start. So when t equals 0, we want to find what p is. So p is going to be 30,000 e to the power of 0, because 0.1 times 0 is 0. E to the power of 0 is 1, so that means we're starting off with 30,000 people in this particular city. Part B, find the rate dp dt. Okay, remember the rate is population with time, and then show that this is true. So let's start with that first bit. So dp dt means we're going to take this equation and we're going to differentiate this with respect to t. Now remember, constants just stay there, so we're going to write 30,000 times. Now when we go to differentiate the exponential, remember you take the power, differentiate that, and that goes in the front. So 0.1t times the derivative of 0.1t is 0.1, so 30,000 times 0.1 e to the 0.1 t. What we can then do is evaluate the numbers, and we get 3,000 e to the 0.1 t. So that's the first part of the question. Part 2, show that this is true. Now if I were to start with this step, so let's come back to this, dp dt equals to 30,000 times 0.1 e to the 0.1 t. Now, instead of evaluating this, because I want p, we know p is 30,000 e to the 0.1 t. We can already see that there, 30,000 e to the 0.1 t. So what I'm going to do is I'm going to swap these two numbers around, because in a multiplication we can multiply them in any order. So I'm going to write that as 0.1 times 30,000 e to the 0.1 t. And you can see that this bit here is p. So then this is 0.1 times p. So this is the special equation that we use for exponential growth and decay. Okay, so when something's increasing or decreasing exponentially, that's the format that your equation will look like. You'll never be asked to start with this and end up with your normal equation. They'll usually give you some extra steps in between to get there. Or they might tell you, here's the question, prove that this is true. Okay, and to do that, you would do the working out. Okay, so that's the sort of working out you'd be showing. So we found an equation, a formula, to find the rate of change. Okay, so how quickly the population is increasing or decreasing. Part C, at what rate is the number of people increasing after 4 years? So we're looking for a rate, so we're looking for dp dt. So the aim of this question is when t equals 4, we want to find what dp dt is, okay? So what is the rate of the increase? Okay, that's your rate of increase, but we want for 4 years. So let's put the numbers in. So dp dt from before is 3,000 e to the power of 0.1 times 4, and that's what you're putting into your calculator. So 3,000 e to the power of 0.1 times 4, and that should give you 4,475.47. Now, because we're talking about population, we need to round that to the nearest whole number. Okay, it makes no sense to have half a person. So that's going to be 4,475 people. And because it's a rate, remember, it's people over the time, okay? And the time was in years, so it's 4,475 people per year. Okay, so just make sure you check carefully what the units are. It's always best to write your units back in. Part D, what was the average rate of increase over the first 4 years? That word average is really important. So average, we're looking at the difference from beginning to end, starting to the finishing, compared to, so the population between start and finish compared to the time between start and finish. So what we're actually looking for here is a gradient, okay? So it's a gradient of a straight line. So what we need to do is we need to work out what the population was at 0 and at 4, okay? So t equals 0, we need to work out p, and we did that before, it was 30,000. And when t equals to 4, we also need to work out a population. So that would be 30,000 times e to the power of 0.1 times 4. So when you go to calculate that, 30,000 e to the 0.1 times 4, it's 44,754.74. Again, round that to the nearest whole number, 44755 people. So what that means is when we're looking for average, we're looking at gradient. So the gradient is going to be the difference between our two p numbers, population, over the difference in our time. So 44755 minus 30,000 over 4 minus 0. So 44755 minus 30,000. If we divide that by 4, that's going to be 3,688.75, or that's 3,689. Again, people per year. Okay, so the average rate of increase, what we're looking for is over those 4 years, how many people are we increasing by per year if it was the same the whole way through. But you can see in that 4th year, okay, so after 4 years, the rate is actually much higher. So it sort of tells us that initially it was a little bit slower and then it's been increasing over time. Or in other words, if we were to draw a diagram of this, exponential looks like this. And what we're looking at is if that's your value of 30,000 and that's where time is 4, the value that we've found in C is the tangent here. So how much has it increased by in per year? Whereas what we've calculated with the average rate of increase, we've looked at these two numbers and we've drawn a tangent in, and you can see the tangent's a lot flatter. Okay, so over those 4 years, how much has the overall value increased by? So be very careful with how the question is worded. Average rate of increase means you're doing a gradient calculation. If you're looking for a rate of change, then you are doing a differentiation question. Okay, last part. After how many years did the population double and what was the rate of increase then? So we know that we initially had 30,000 people. So if we want to double the population, we want P to now equal to 60. So what we're going to do is we're going to make P equal to 60,000. Let P equals 60,000. So then your equation is 60,000 equals to 30,000 e to the 0.1t. What we can do is we can divide the 30,000 over. So that'll be 2 equals e to the 0.1t. And then we want to convert this into a logarithm. So that's going to be 0.1t, the power, equals log e2. Or we could write that as ln. All we've got there, if we divide by 0.1, 1 over 0.1 log e2, and then you want to put that into your calculator. So don't forget to use the ln button, not the log button, and you should get 6.93 or thereabouts. So after how many years did the population double? We would have needed to get to 7 years, okay? Because if I chose 6 years, it hasn't quite doubled yet. So after 7 years, the population will double. Now we need to answer the second part of the question. What was the rate of increase then? Now, we can actually go back up here and we can actually use this equation right here because we know what the population is. So if we know what the population is, we can calculate this rate straight away. So what we could do with this is we could say when P equals to 60,000, then dP dt is 0.1 P, which is 0.1 times 60,000, which comes out to be 6,000 people per year. So that's sort of like a shortcut way you can use to find the rate of increase. Fully valid, nothing wrong with that answer. Or what you could do is you can substitute this into the equation to work out what the rate is. So if you put 7 years in, obviously it's not going to be perfect 6,000 people because we have rounded this number off. But if we use this exact value and we substitute into that rate formula, we should get pretty much close to 6,000 there. So just a couple of questions to work through. So they're all to do with exponentials. You will need to differentiate a couple of them, so make sure you remember how to do that. And a lot of this will be about interpreting a worded question and also knowing the difference between the average rate of change and your actual rate of change.